Good morning, class. We are looking at Module 2, covering Chapters 3 and 4. Chapter 3, and rational functions. Chapter 4, exponential and logarithmic functions. First, I want to remind you, before starting the exam, please read the following pledge. I pledge on my honor that I will neither give nor receive unauthorized assistance during this or any other exam. Unauthorized action include, but are not limited to, the use of notes, text, graphing calculators, search engines, PowerPoints, AI, or any other resources not explicitly allowed. So we are looking at Chapter 3, Polynomials and Rational Functions, and here's the first part. So the price-demand function of a company that manufactures tops is P of x equals minus 5x plus 600. Find the revenue function R of x. By definition, the number of units x times the price would be R of x. So we get minus 5x squared plus 600x. The company's fixed monthly cost is $1,563, and each unit of tops costs $10. Write the cost function C of x, where x represents the number of packets of tops produced. In general, we are looking at the concept of y equals mx plus b. Where here, y or f of x is c of x. M, the slope, is the $10 cost per unit, the varying charge. And b, the y-intercept, and now the c-intercept is the fixed cost. This is the fixed cost. So b is 1,563. Therefore, c of x is 10x plus 1,563. The profit function. Profit, by definition, is the difference between revenue and cost. So simply subtract the cost from revenue, which means you're going to write the revenue function minus 5x squared plus 600x minus, going to distribute, and we get minus 10x minus 1563, and these two are like terms, and we put everything together, we end up with the profit function is equal to minus 5x squared plus 590x minus 1,563. How many tops must be produced and sold in order to maximize profit? Well, we want to maximize the profit, so we look at the profit function. Obviously, this is a quadratic function, where a is -5. So remember, parabola looks like that. This one looks like that because it opens down. So the maximum occurs at its vertex. So the quadratic function is in the form of ax squared plus bx plus c equal to 0. The vertex, the x coordinate of the vertex has the equation minus b over 2a. This is a quadratic function with a being negative. It doesn't matter what the number is. We want the sign. That means it opens down. That means x equals minus b over 2a. So this is a. This is b. So x equals minus b over 2a minus 590 over 2 times -5. The answer is 59. So 59 tops will do the job. What is the maximum profit? Here's the profit function. Replace the x with the number we just got, which becomes P of 59 is minus 5, 59 squared plus 590 times 59 minus 1,563. And when we put it into a calculator, we end up with $15,842. What price must the company charge in order to maximize profit? We go back to the very beginning. Here's the price function. Replace the x with 59. So P of 59 means minus 5 times 59 plus 600. We get $305. The polynomial of degree 3, P of x, has a root of multiplicity 1 at x equals minus 6 and a root of multiplicity 2 at x equals 4. P of x passes through the point x comma y 2 comma 8, and we want to find the formula for P of x in factored form. So first and foremost, reminding you what is a polynomial function. Polynomial function. A polynomial function of degree n in the variable x is a function defined by P of x equals a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 all the way to plus a sub 1x plus a sub 0, where each a sub I, the coefficients, is real, and the first one, a sub n, can't be 0, and n is a whole number, 0, 1, 2, 3 to infinity. A sub n is called the leading coefficient. A sub n x to the power of n is called the leading or dominating term. A sub 0 is called the constant term, and in essence, it becomes the y-intercept. P of 0 equals a sub 0 is the y-intercept of the graph of P of x. So that's just to remind you what's happening. As far as setting up a polynomial, giving its roots or zeros or x-intercepts, they are all referring to the same concept. So when we say x equals minus 6, in general, when we say x equals k, that means x minus k is a factor. When we discuss multiplicity, when we say multiplicity is 2, that means the exponent here is 2. Therefore, we are going to write the polynomial P of x is, we start with some constant which we don't know what it is. So we're going to call it a. And then this one means we have x plus 6. This means we have x minus 4. This one has multiplicity 1, so the exponent is 1. This one has multiplicity 2, therefore the exponent is 2. So take a look. P of x is a, because we don't know what is the leading coefficient. X plus 6 is because of this. The exponent is 1. We don't have to write because of the multiplicity. And x equals 4 results in x minus 4. Multiplicity 2, that gives us the exponent. Now we have one pair and we can plug in and find the missing a. 2 comma 8, that means 8 is the y coordinate, or P of 2. So P of 2, if I replace this with 2, I get a times 2 plus 6 times 2 minus 4 quantity squared equals 8. Now, needless to say, they add up to 8. These 2 to negative 2. And I can drop the 8 from both sides, and this becomes 4, meaning 4a equals 1. A becomes 1/4. Replace it, and the function P of x is 1/4 x plus 6 times x minus 4 quantity squared. Divide using synthetic division, express the answer as f of x over d of x equals q of x plus r of x over d of x. 3x cubed minus 2x squared plus x minus 4, 1 divided by x plus 1. So in general, division of a polynomial by x minus k, if the degree n polynomial p of x is divided by x minus k, remember, this has degree n and this has degree 1, right? Then the quotient polynomial q of x has degree n minus 1. So it goes down by 1 because this has degree 1. The remainder r is a constant and may even be 0. The complete quotient for p of x over x minus k may be written as follows. P of x over x minus k equals q of x plus r over x minus k. For example, 3x cubed minus 2x plus 5 over x minus 3. We go through the process. We get 3x squared plus 9x plus 25 plus 80 over x minus 3. So the top, the numerator, is the dividend. The bottom is the divisor. This is the quotient. This is the remainder. And of course, this is the divisor. And this is the fractional part. So this is the details as far as this methodology. Now, for synthetic division, we are going to make sure this is in descending order. So highest degree starts and it goes down. And then we just write the coefficients, 3, minus 2, 1, minus 1. Also, if any term is missing, you put 0 as a placeholder. For example, this didn't exist, we would put 0. So over here, for example, the numbers would be 3, 0, minus 2, 5, but over here would be 3, minus 2, 1, minus 4. Because we are dividing by x plus 1, we put a minus 1 in the following manner. So we have the numbers in order, and negative 1 is right here. And so we drop the first number, 3, as it appears. We are going to multiply by negative 1. So if I multiply by negative 1, I get negative 3. I add them up, and it gives me negative 5. We continue with this process. Negative 5 times negative 1 becomes positive 5. We add these two, we get number 6. 6 times negative 1, negative 6. Add them up, negative 10. And therefore, when we look at this one, we recognize the quotient as 3. This is x cubed. This goes down by 1, 3x squared, minus 5x plus 6. What is this? The remainder. You can say the remainder is minus 10, or add negative 10 over x plus 1. So 3x squared minus 5x plus 6 plus negative 10 over x plus 1, or just write minus either this or minus 10 over x plus 1. That's your choice. Consider the function f of x equals 2x cubed minus 8x squared plus 5x plus 3. List all the possible rational zeros of the function f. So what is the rational zero theorem? According to the rational zero theorem, if there is any rational root, then it would be factors of a sub 0, the constant, divided by factors of a sub n, in this case would be 2. So factors of 3 over factors of 2. Recall f of x is a sub n, x to the power of n, all the way to a sub 0. This is the leading coefficient. This is the constant. So therefore, we're going to write factors of 3 over factors of 2. So factors of 3 obviously are plus minus 1 plus minus 3. For 2, plus minus 1 plus minus 2. And I hope you see, if you divide the top by plus minus 1, you get the same thing. If you divide by the bottom, you get plus minus 1 half plus minus 3 halves. And so those are the possibilities. Bear in mind the process is as follows. We want to find the rational zeros of f, the function f of x. So the process is as follows. You plug in each one and see which one gives you 0, because according to the remainder theorem, if a polynomial p of x is divided by x minus k, the remainder is equal to p of k. So for example, if I plug in 1 and I get 7, that means if I were to divide by x minus 1, I get 7. That's the meaning of it. Okay. Factor theorem. The polynomial p of x has a factor of x minus k if and only if p of k equal to 0. Now, when you do that, if it results in 0, that means that must have been a factor. Okay, so x minus k must have been a factor. So to do so, we have to plug in negative 1 half, positive 1 half, negative 1, 1, and so forth. And normally they start with easy numbers like 1 and negative 1. I'm not going to go through that process, but that is the proper methodology to do that. So I'm going to plug in 3, and it so happened that is going to be 0. 2 times 3 cubed, which is, let me just erase the work here, everybody, which is 27, and therefore 54. This is 9, therefore minus 72. This is plus 15. And if you add up the numbers, you end up with 0. If f of 3 is 0, the remainder, when the remainder, it's really the remainder theorem, when it becomes 0, that means it becomes a factor. What becomes a factor? X minus k, x minus 3 is a factor. So we already have one. Since this is degree 3, if we divide by x minus 3, it goes down by 1, it becomes quadratic, and we know how to handle quadratic, either factoring or the quadratic formula. So you don't have to continue with that. It's your choice in essence. And so find the remaining zeros. We are going to divide the original function by x minus 3. So to do so, let's go with the synthetic division, and this has to be in descending order. It is 2 minus 8 positive 5 3, and nothing is missing, no term is missing, and we're going to put it 3 there. So we're going to drop number 2 just the way it is. We're going to multiply these two, and we put it here. 6 and negative 8, they add up to negative 2. We're going to multiply by 3, and we put it here, we get minus 6. They add up to negative 1. We multiply by 3 again. You keep on multiplying by this number, okay? And you get negative 3. As expected, they add up to 0 because we know already it's a factor x minus 3. So what do we have? This is 2x cubed, so this must be 2x squared. We go down by 1. 2x squared minus 2x minus 1, okay? And this is easy to handle. It can't be factored, but the quadratic formula indicates that ax squared plus bx plus c equal to 0. X is minus b plus minus a squared of b squared minus 4ac over 2a. So a is 2, b negative 2, c negative 1. Plug in. So this is positive 2, this is positive 4, this is positive 8, 4 and 8. This is 4, this is 8, so that gets 12. 12 is 4 times 3, so this is 2 square root of 3, and this 2, we can factor the 2 out, we get 1 plus minus square root of 3. So the 2 goes away, 4 becomes 2, 1 plus minus square root of 3 over 2. Factor f using the zeros of f, and so obviously we already know one of them is x minus 3. How do we write the rest of them? Check it out. F of x is x minus 3 times x minus 1, the parentheses, 1 minus square root of 3 over 2, x minus the parentheses 1 plus square root of 3 over 2. That's how you write it. Which of course indicates when we went through this process, there was only one rational zero. And by the way, the rational zero theorem says if there is any, and there may be none, if there is any, has to be among those. And of course, 3 is one of those. That's the idea. And I hope everybody is fine with that. Consider the function f of x equals x to the power of 4 plus 2x cubed plus 22x squared plus 50x minus 75. Find f of 1, find f of negative 3. We just have to plug it. And I'm reminding you of the rational zeros by its factors of a sub 0 over factors of a sub. So having said that, we plug in 1. So we get 1 to the power of 4. This is 1. 1, all of them are 1 times the number. So in other words, this is 1 plus 2 plus 22 plus 50. They add up to 75. Minus 75, 0. Now, I'm going to leave it for you to evaluate f of minus 3, plug in, and you do get 0 also. So again, you have to just plug it in and evaluate it, everybody. I'm going to, as I mentioned, I'm going to leave it for you to do so. If we were to use rational zero theorem, would be factors of negative 75 over factors of 1, right? This is the constant, and this is 1, the leading coefficient. Factors of 1 is plus minus 1, so the result will be only factors of negative 75, and that would be plus minus 1, plus minus 3, plus minus 5, plus minus 15, plus minus 25, plus minus 7. There are a lot of factors to check, but that's just the methodology. If we were to use technology, there are a couple of ways. Graph, second, calc, 0, or try these numbers one by one. You can put this into a function and evaluate it at these numbers, and it does it pretty fast. And you can figure it out. Now, it's important to know that we already have 2 of them, and by the way, it's easy to find the rest of them. However, if 5i is a 0 of the function, find the remaining zeros of the function. So, what do we need to know? This is important. Number of zeros theorem. A function defined by a polynomial of degree n has at most n distinct or unique complex zeros. Remember, the multiplicity adds up to n. Also, conjugate zeros theorem. If p of x is a polynomial with real coefficients, and if r equals a plus bi is a 0 of p of x, then its conjugate r bar or r star or r prime, depending upon the text, a minus bi is also a 0 of p of x. So if in general a plus bi is a solution is a 0, is a root, so is a minus bi. So because 5i is given, so is negative 5i. Okay, that is known as the conjugate zero theorem. Therefore, we want to factor f of x using zeros of f. It's very simple. F of x is, well, this one says x minus 1 because f of 1 is 0. This says x plus 3. This is x minus 5i. This is x plus 5. And by the way, if we were to multiply, the methodology of multiplication is that to remember a plus bi, a minus bi is a squared plus b squared. The product of these two is x squared plus 5 squared. That means plus 25. This is how you do the multiplication if need be. Find the domain of the following function. Express your answer in interval notation. As always, in the case of a rational function, you set the denominator equal to 0 and you exclude. X squared minus 2x minus 8 equals 0. Now, to factor this, remember you want two numbers. The product is negative 8. The sum is negative 2. That would be positive 2, negative 4. So x is either negative 2 or positive 4. Again, it's important. These are the two numbers that make the denominator 0 must be excluded. Therefore, we write from negative infinity to negative 2, parentheses, union, negative 2 to 4. Both of them take parentheses, union 4 to infinity. And when you use parentheses, that means the endpoints are not included. Use the remainder theorem to evaluate f of x equals 6x to the power 4 minus x cubed minus 15x squared plus 2x minus 7 at x equals, simply put, plug in f of 2. 6 times 2 to the power of 4 minus 2 cubed minus 15, 2 squared plus 2 times 2 minus 7. That's it. And we are going to evaluate this. So this is 16, 6 times 16. This is minus 8 minus 15 times 4. This is 4. 6 times 60, 96, minus 8, minus 15 times 4, 60, 4 minus 7. And you add them up, you get 25. All right. Show that x plus 2 is a factor of x cubed minus 6x squared minus x plus 30. Find the remaining factors. Use the factors to determine the zeros of the polynomial. Well, To show this is a factor, we have to, we call this f of x. We're going to evaluate the function at -2, f of -2, which means -2 quantity cubed minus 6 times -2 squared minus -2 plus 30. And so minus 8, this is positive 4 minus 24 plus 2 plus 32. I hope you see that it's -32 plus 32, that's 0. That's a proof. If f of -2 is 0, then x plus 2 is a factor of that. So to find the remaining factors, well, we're going to divide by x plus 2. To divide by x plus 2, we make sure this is in descending order. And we use the coefficients for synthetic division. 1, minus 6, minus 1, and 30. And nothing is missing. Again, for example, this is missing, you would put 0, okay? And we are dividing by x plus 2, we're going to put -2 there, just as we did here. So we drop the first number. Then we multiply these two. Let me just write the first one. So we are going to multiply by -2, and we get -2. We add them up, we get -8. Multiply by -2 again, we get +16. We add them up, we get +15. Multiply by -2, we get -30. As expected, they do add up to 0. Which means when we divide this expression, the polynomial function, by x plus 2, we get 1x squared, or simply x squared, minus 8x plus 15. So we write x cubed minus 6x squared minus x plus 30 is x plus 2 times x squared minus 8x plus 15. And we recognize this is a very easy factoring because we want two numbers. The product must be 15 and the sum must be -8. So both of them are negative, -3, -5. So x plus 2 times x minus 3 times x minus 5. Okay. So therefore, according to the factor theorem, x equals -2, x equals +3, and x equals +5. Those are the zeros. So we're going to write by the factor theorem, the zeros of the polynomial x cubed minus 6x squared minus x plus 30 are -2, +3, +5, accordingly. Given the function f of x equals x plus 4 over 2x squared plus 11x plus 12, find the domain of f in interval notation, so on and so forth. We are dealing with a bunch of steps. The purpose of this is to graph it ultimately. And the very first thing you do with any fraction or a rational expression or a fractional expression, you ask yourself, can I simplify? That's the first. And by the way, simplification, if there is a factor of x plus 4 here, it can be simplified. Otherwise, it cannot be. So you can actually check with x plus 4. In other words, you can say, okay, what if I happen to have a x plus 4 there? If it happened to be x plus 4, this must be what? 2x. This must be what? 12 divided by 4 plus 3. It happened to work out. How do we know it works out? Check this out. The middle term is important to work out. So if I multiply these two, I get 8x. Let me just erase everything. So if I multiply these two, I get 8x. If I multiply these two, I get 3x. Do they add up to the middle term, 11x? They do. It works out. I'm going to erase my work again. So we drop the common factor, and we get 1 over 2x plus 3. However, x can't be negative. I want to explain this one. First of all, even if there is more common factor between the two, it doesn't change the domain, everybody. That's the first thing I want you to see. X can't be negative 4, and x can't be negative 3 halves from here. First, I want to discuss the domain. So we are going to write from negative infinity to negative 4, union negative 4 to negative 3 halves, union to negative 3 halves to infinity, meaning we are excluding both numbers. X equals negative 4, x equals negative 3 halves again. So the way you find it, I want to make sure we understand. X plus 4 equals 0. That means x equals minus 4. 2x plus 3 equal to 0. That means x equals negative 3 halves. These two create a problem. They give us a 0 in the denominator, and we got to get rid of it. That's the idea. And the way you write interval notation, always from small to large. Now, it says find the asymptotes as well as any holes. Now, the very first thing actually I want to discuss would be the holes. If you, let me erase my work again. If you happen to have a common factor between the top and the bottom, and you drop it, and then it's important to pay attention to this, x can't be negative 4. At common factor, it creates a hole. So if you plug in negative 4 here, so x equals negative 4, what is y? If you plug in here, it gives you a pair. So this function doesn't have a hole, but with this function, which has this added explanation, it creates a hole. So again, if we didn't have this, this was missing. This function has no hole, but this one does. Where do you find the hole? Put negative 4. 2 times negative 4, negative 8, plus 3, negative 5. 1 over negative 5, which means negative 4 comma negative 1/5. That is the location of the hole. So 4 to the left and 1/5 down. So this may not be exact, but that's roughly the where you find it. Now, how do we find VA, short for vertical asymptotes in general? Set the denominator equal to 0. This one, no. The one that is simplified. In other words, you can't say x equals minus 4 is the equation of a vertical asymptote. That is where the hole happens. So the simplified version, the denominator is equal to 0, x equals minus 3 halves is the equation of a vertical asymptote. You draw that. Minus 3 halves is minus 1.5 between negative 1 and negative 2. Now we want to find other asymptotes. What are other asymptotes? Well, If you have a rational function, numerator over denominator f of x is a sub n x to the power of n all the way to a sub 0, and b sub m x to the power of n plus all the way to b sub 0, what you're dealing with is a rational expression. If n, the degree of the numerator, is less than m, the degree of the denominator, horizontal asymptote has the equation y equals 0. In fact, right here, the degree of the numerator is 0. The degree of the numerator is 0, the degree of the denominator is 1, and that indicates y equals 0. But let's continue. If n equals m, in other words, the degree is identical, the leading terms will take over ultimately as n goes to infinity or negative infinity. And so the ratio of a sub n to b sub m, that is the equation for the horizontal asymptote y equals that. And finally, if the numerator has a degree which is larger than the denominator by precisely 1, in other words, n equals m plus 1, you do long division, synthetic division, and you end up with mx plus b, and then some remainder. Y equals mx plus b represents oblique asymptote. So having said that, as I mentioned here, horizontal asymptote has the equation y equals 0. There is no oblique asymptote. By the way, you have only one of it. And of course, the y equals 0, that means the x-axis. Even if they don't ask you, you always have to look for intercepts, always. And I want to remind you that if you have a fractional format a over b, a fraction is 0, a over b is 0 if the top is 0, a equals 0, and is undefined otherwise. Okay, so it's important to understand that. So for the x-intercept, I'm going to go back to this one. I set y equal to 0. So a fraction is 0 if the top is 0, but the top can't be 0. Why not? Because it doesn't have any variable. So x-intercept, none. Y-intercept, if I replace the x with 0, I get 1/3. So 0, 1/3, between 0 and 1, and 1/3 of the way, roughly. Again, it may not be precise, but that's fine. Now, it's important to understand that we have the horizontal asymptote, we have the vertical asymptote. If we were to graph it, on the right side, either like this or like that, on the left side of the vertical asymptote, the same thing. So it's really a good idea to locate at least one point on each side. For this side, we really don't need it because 1 point we have, so it's essentially this one. For this side, this whole actually gives you an idea, but let's go with easy numbers. -2 and -1 result in easy results. So if I put -2 in here, I get -4, +3, -1. 1 over -1 is -1. If I put -1, I get -2, +3 is +1. 1 over 1 is 1. So those are the pairs. Plot those, put them together. There's your graph, and you're done. Given the function f of x plus 1 times x minus 5 over x minus 3, find the domain of the function, of course, in interval notation. So simply put, x minus 3 is 0, x equals 3 must be exclude. So x cannot be 3. So quickly, so from -infinity to 3, union 3 to infinity. What about the asymptotes? Vertical asymptote is very easy, x equals 3. There is no horizontal asymptote. So x equals 3. I'm going to go and say, okay, this is 2. So each tick mark is 2. So somewhere here between 2 and 4, x equals 3. Now, to find whether or not we have an oblique asymptote, we're going to multiply these two. Please understand this one is x squared and this one is minus 5. In between positive 1 and negative 5, they add up to negative 4. We get x squared minus 4x minus 5. So we are going to divide the top by the bottom using synthetic division. So this is 1 minus 4 minus 5. And this one we're going to use positive 3. When we divide by x minus 3, we put positive 3 here. Which means we're going to drop the 1. Multiply these two, we get 3, and we put it here. Add them up, we get negative 1. Multiply it again, we get negative 3. Add them up, negative 8. Which means, so this was x squared, this was x. So this is 1x minus 1. So the answer is x minus 1 minus 8 over x minus 3. Which indicates what? Y equals x minus 1 is our oblique or slant asymptote. There is no hole. Why not? Because there is nothing in common. So there is no hole because there is nothing in common. So we draw that, and just to give you an idea, everybody. Obviously, 0 minus 1, remember between two, so 0 minus 1 is here, and then if you plug in, if y is 0, x becomes 1. 1, 0 is here, 0 minus 1 is here. So roughly, this is the graph. Again, it doesn't have to be to scale, but it's close, okay? Now, obviously, we want to find the intercepts, even if they don't say so. So x-intercepts where is it? Let me again erase my work. I'll go back to original one. If I put f of x of y equal to 0, that means the numerator is 0, right? Remember, this is 0 if the numerator is 0. So x is minus 1, x is positive 5. So minus 1, 0, 5, 0. So this is negative 2. This is negative 2. And this is positive 2. So in between, and then 5, 0, this is 2, this is 4, this is 6, so in between. So we have those. Y-intercept, it's easier to go this route. This one, and this one are 0 because you replace the x with 0. So you get negative 5 over negative 3, which is positive 5/3. So 0, 5/3. Okay, it's somewhere here. It's a little bit off here, but you get the picture. And so now we want to graph them. We put them together. They look like this. We have the vertical asymptote, the oblique asymptote, and this actually goes like that. But just to give you an idea, this runs along and this runs along, okay? So that would be the end of the graph.